We are going to sort these numbers in increasing order. We're going to use the heap sort algorithm. The heap sort algorithm has two phases. The first phase is we need to put all these numbers into a heap tree. And the second phase is we are going to pluck or remove the root node of this tree successively and replacing the root node with the last number that we put in. To recall, a heap tree is a binary tree with a property wherein the parent has a bigger value than its two children. We need to enforce this property in a heap tree. So a heap tree has a node which has two blank slots, the left and the right. And once all these two slots are occupied, then the free slot is in its children. So first we read 2. We now have a heap tree with one element, 2, which is the parent. We read the second number, which is 3, and we put this into the free slot, which is the left side of 2. After putting 3 into the left side of 2, we enforce the property of the heap, which is the parent should be bigger than the child. And we will continue to enforce this property until every node has this property. So we read in 3 and we swap them. The parent should be bigger than its child. That is a property of the heap tree. Next, we read in 4. The free slot is on the right side of 3. We put 4 there as a right child of 3. But because 4 is bigger than its parent, then the child and the parent needs to swap. There. Now we have a small tree which is having the parent of 4 and a 2 child, 2 to its left and 3 to its right. This small tree is fully booked. The free slot now is on the left side of 2. That is the next free slot. So we read the number 1 and put it there. And no swapping occurs because the property of the heap is enforced, which means the parent is bigger than its child, which is true here. For example, the parent 4 is bigger than its two children 2 and 3, and the parent 2 is bigger than its only child 1, and the parent 3 has no children. So all is well. Now the next number to read into the tree is 5. The free slot is in the right side of 2. We put 5 under as a right child of 2. And after putting that, we enforce the property of the heap tree. Because 5 is greater than 2, then they need to swap. After swapping, 5 becomes the left child of 4. But because 5 is greater than 4, then they will swap further. Swapping stops when the property is enforced in all the nodes. There. So we have 2 swaps there because we need to enforce the property. And that property is saying that the parent should be greater than its child. Let us examine now. The parent 5 is indeed greater than its two children 4 and 3. Next, the parent 4 is indeed greater than its two children 1 and 2. And the parent 3 has no children. So as we can see, the property of the heap sort is enforced. It is correctly enforced. Now we read the number 6. The free slot is on the left side of 3. After all, this is a binary tree. A node has only 2 child left and right. And 3 is a parent. It has a free slot on its left node. We put 6 there. After putting 6 there, since 6 is greater than 3, then they need to swap. And 6 will become the right child of 5, and they will swap further. And swapping stops until the property is enforced. There. As we can see, there were two swappings to occur in order to enforce the property. If we examine the tree all over again, we can see that the parent 6 is indeed greater than its two children 4 and 5. The parent 4 is indeed greater than its two children 1 and 2. And the parent 5 is indeed greater than its single child, which is 3. Okay, all is well. Now we read number 7, and the next free slot is on the right side of 5. We put 7 as a right child of 5. 7 is greater than 5, so they need to swap. After that first swap, 7 becomes the right child of 6. Because 7 is greater than 6, they will swap one more time. Okay, swapping stops when the property is enforced, and indeed the property is enforced here. We have a complete tree. At this phase, we read all the elements in the array into the heap tree, and the property of the heap tree is enforced. Let us examine. The parent 7 is greater than its two children 4 and 6. The parent 4 is greater than its two children 1 and 2. And the parent 6 is greater than its two children 3 and 5. So we have a binary tree having this property wherein the parent is greater than its two children left and right. This is a heap binary tree. We have completed phase 1. Now let us go to phase 2. Phase 2 will remove the root node, and the root node becomes vacant. The last element that we read into the tree will replace the root node. The last element is 5. When we remove 7, 5 will take the position of the root. And once 5 has replaced 7, then we do the enforcement, meaning we swap so that the property is enforced. Imagine now that 7 is removed and 5 is there. Its two children 4 and 6 is greater than 5. In this scenario, the swap will occur to the one that is greater. So that will be 6. There. Even though 4 is also greater than 5, but the swap is on the 6 because that is the greater number. And as we can see, 7 is now removed and we now have a smaller tree, but with the properties enforced. Next again, we remove 6. We always remove the root node. And then the last number that will replace the root node is 3, because that is the last element that we post in reverse order. Imagine now that 3 will be taking the place of 6, and 3 has two. The parent 3 has two child 4 and 5, which is greater than itself, but the bigger of this is 5, so it will have to swap with 5. There, it swaps with 5, and we now have a much smaller tree. But in this smaller tree, all of the properties are enforced because of the swapping. We remove 5, and 5 will be replaced by 2, and 2 will need to swap with 4 because 4 is the greater. There. Now we remove 4 and replace it with 1. Okay. And then we remove 3. We always remove the root node in phase 2, and it will be replaced with 1. Now we remove 2, and then lastly we have a 3 with only single node 1, and we remove it. As a result, we now have a sorted list of numbers